or something in between. At least give you some choice, right? Questioning and pre-questioning, and then some calculation. It cannot be too difficult, too simple. At least something in between. I think I need to be practical. Yeah, and also think. Of course, after this midterm, I do hope that we will. I do hope that we have no final to do some project to see if you can try to do some interesting project. I need to give you some interesting some online tool for VR AR tool. It's for kids, but I believe it can also use for university students, so that this CodeSpace we use CodeSpace online tools be used for at least year 6 student now in our Clearwater school next to this UST, so that you know we have one private school next to UST, right? So they're using. Let me show you this interesting this kind of CodeSpace for you to think about. If you do something, you want to quickly build a 3D model. It's interesting. The low key can you build a 3D model? Very impressive. Of course, this is not. I didn't ask you to play this one. Right? It's really for us. We want to build this kind of physics-based, this kind of model simulation. For you see here, they do have this kind of thing. If you go to this, and then you see, they can really do some quite interesting simulation about this kind of physical simulation for a certain of this kinds of. You see. If you go here, then you look at their model, and then to see, wow, personally, I surprised that they can really come with a pretty simple way to do things. Fire. This is the physics base, right? So you can adjust velocity, the way MCK system, and you can try to look at this kind of a response. And then it's something, you see, this is more intuitively, right? We just try to do some simple calculation, but now with this kind of online tool, my God, you can really play this one and then try to see about the result. And then, with the ball, too fast, the speed too fast. Fire. Okay. Oh. Oh, too fast. Anyway, so it's a very spatial. They can do all this interesting, like a model, physics-based simulation, It's pretty impressive, I would say. You can see that how Newton's law, Why we are trying to do some kind of simulation, anti-gravity room. You cannot go to the space station, but how about do this kind of simulation and then try to see what happens. And then you turn off the gravity. Huh? It's it's quite interesting to play this physics, right? In this kind of okay. Yeah, I would say I'm surprised. This is for the little kid, but what do you think? They can also do coding. Coding, you say, it makes some coding and then try to see. It's a pretty interesting, no, thing for all the things, huh? I personally, I'm a little surprised. This kind of online tools can be really, huh? Huh? Quite surprised to see that they can, you can, okay. Anyway, so it's something interesting for all of you to think about this kind of free, at least more free source, right? Okay, and of course, I don't do any question. I think if no question, we need to continue our lecture. Okay. So last time we already talked about this kind of chapter 5, right? We have go beyond this kind of thing, and then so that so I just try to give you quickly. Of course, I think I do want to skip some of quite complicated mathematics, right? So that because all of you has this kind of lecture note, but I just to try to quickly show you some basic concept, and then I will not go too much complicated mathematics thing, but tell you about the concept of this thing, and then how can you do some more this kind of engineering, right? More practical stuff, right? And so the user, this thing is all of you can look at the lecture note, but I do want you to try to look at those kinds of the content of our lecture note, and then you can ask some question to now about some of this material in the lecture note. Again, we have talked about this kind of two-degree freedom problem, right? And then the key question is I do hope that you understand. So for different engineering, we may require different kind of model, right? So that this thing is I already show you some example on this aerospace engineering, right? Rocket problem, and then of course we show you about how we can use this kind of the right equation motion, right? So that we have two mass, we can describe this kind of MK, right? M is 2 by 2 mass matrix, K is 2 by 2 stiffness matrix, and then in this case we give you initial condition, and then we can solve this kind of differential equation either by, if too difficult, then we can solve by hand. Right? If too big, and then what happens? We solve by computer, MATLAB, so that something is a piece of cake, right? So that's how we under harmonic vibration, then we can reduce this kind of differential equation into what? Linear algebraic equation. That is key, right? So that the linear algebraic equation, and then this become what? Eigenvalue problem. You learn in proper linear algebra in our UG math course, right? And the key thing here is we in this problem, what is a known? U is a vector, vibration amplitude vector, right? And then these are known. And then what else is known? This is a known. So that and then given this kind of mechanical system, our mass and spring or stiffness matrix, how can we determine this unknown? Why? So that we can already describe basically we try to solve this one into the eigenvalue problem, and then eventually for 2 by 2, and then we can easily try to what, get the determinant of this matrix and solve for unknown omega, right? And eventually become the second order quadratic equation, and then unknown is omega squared, and eventually we can determine this kind of natural frequency, I would say, right? And in general, there are 4 natural frequency, plus, minus, and seeing, right? So that we can get this result. And of course, we also mentioned that eventually this kind of thing is what? Basically, this is if a 2-degree freedom, right? 2-degree freedom system, so that the 2-degree freedom, 2 DOF system, we have M1, M2, and then we have what? 2 natural frequency. So this is an important thing. All of you should have no problem to understand this thing. But of course, one student asked a good question. Why? So that of course we have 2 solutions, total 4 solutions, right? So that we have this one, and then -1. So most likely you probably can never find any mechanic system MCK or MK who have a negative frequency, which doesn't exist in our real world, right? The same thing, you have this kind of a positive 2 and -1. So that in this case, we can think about this -2 is not the, it doesn't exist in the real world. But on the other hand, if you look at our solution to solve this kind of equation motion, why we use complex number. Complex number, so that in this case, this in general, we have what? We assume our U, remember, I assume U, right, is my vibration amplitude equals U to the this kind of omega t. Why this omega? So that in this case, in general, we use complex number to describe this kind of vibration amplitude vectors. So that in order to get the general solution for this, actually we still need to get the this old solution now to construct this kind of a general solution, vibration amplitude as function of time. So that that's something. One thing is mathematics. We use mathematics, complex number, to get the solution. Another thing, in real physical world, we have no negative, right? No negative, this kind of negative frequency. So that's something I think we make clear. Why there's no negative, natural frequency in the world, natural frequency in the physical world. Do you understand? So that's it. But we use this kind of complex number to solve our solution, right? So that something is pneumatic. So this is some. I think it's good to see that the student asked the question, so that complex number is our tool, right? With this kind of 4 solution, general solution, right? Each omega solution to the equation motion, right? Simplified equation motion is what? Eigenvalue problem. So in this case, our general solution now will be summation of this four natural frequency with its complex number, right? So that's it. And then with some manipulation based on mathematics, now we can try to reduce this kind of thing into sine or cosine function. So this is something I told you is worthwhile to explain some physics, right? Not only mathematics, but physics about why this is important. We still use complex number to describe this kind of a general solution. Of course, we also mentioned about this vector from this eigenvalue problem is a vibration mode or mode shape, right? So that another thing we can call this vibration mode. Vibration mode. Okay, sorry. Well, we have two vibration mode, U1, U2. Right, so that is something important. And then, of course, we will then show you some example about this problem, and then so that that is of course in MATLAB we can easily solve this problem, right? And then we will show you this is something in reality. You can use MATLAB, right, to do the simulation and also animation. So that is something not challenging. I can provide you some of MATLAB code. I don't know now. Do you know how can you use MATLAB to generate this animation now? Huh? Do you know how to use MATLAB to? Oh, now we solve this kind of now. Huh? Do you have an idea? Huh? Hey, we already give you some. Basically, MATLAB has certain kind of function, right? You know the MATLAB animate is function. Huh? You look at this thing, and then once you can plot this kind of vibration amplitude as a function time animation, so that you can use MATLAB to do this kind of animation. You see, this one, once you can plot, right? Plot this kind of sure. Once you can, let me show you here. MATLAB have this kind of function subroutine, right? So that you use this one, and then you plot a series of these thing, and then you can generate this kind of the plot, and then do the animation. Doing that, so it's something not challenging with MATLAB. MATLAB has this kind of very good tools. Now, let me quickly show you. Actually, this is one of pretty good example, right? Basically, you see, movie. Basically, movie. That means you plot a series. What's a movie? What's a movie? Basically, a series of pictures, right? In play. in maybe 1 second 30 frames, right, or 25 frames. That's the one movie. Basically, that means you ask MATLAB to generate a series of pictures, image, and then play, right? So that is, you see, movie n, and play the movie a number of times, right? Also certify the frame FPS. That's the thing. MATLAB has this kind of function, and let me quickly show you. It's a very piece of cake now. In old day, if you don't have powerful computer, all these are difficult. But now, no, you see, your computer is so powerful, so that it's piece of cake. In old day, 20, 30, 40 years ago, it's not easy, but now it's a piece of cake. Oh, you see? And then let me see. This is a membrane, two-dimensional membrane structure. So that with MATLAB, actually they have a let me see. They have certain kind of basically peaks is built-in function to describe that function, right? And then two-dimensional, right? The thing, right? It's basically, you see, X and Y, and then look at this kind of diffraction of this membrane, right? And then we can try to look at this once you play. You see, H equal figure, Z equals peaks, this function, and plus surface, and then you can show, and then you can look here. So that basically, I don't know if this. and then what? Sorry. Okay, I cannot copy. So I should use this kind of thing. Uh-oh, I need to fix that. Otherwise, it's there's a little trouble to show. You know the problem? The problem is I need to fix that X, Y, and A, so there was no. Try this again. Maybe shut it and then. Okay. Can I make a bit small? Anyway, let me try to play. Oh, it's a shaking. Yeah, I think anyway, I tell you, this is the basic thing that's I think that's I need to do some minor adjustment, right? And then so that it can show anyway, so that you can see we may need to do some adjustment to play the better this kind of video animation. Movie M again. Hopefully it will be better. Sometimes you need to do some tuning about this parameter. Uh-oh. There's certain thing I need to do some adjustment. I understand sometimes it happen. Of course, with the same thing you can try to anyway. I'm pretty sure there's a series of example you try to play, right? The key thing here is you can plot. Now this kind of basically it's a two-dimensional this kind of vibration of a membrane, right? So that if you can plot this kind of, for example, two maps we can show you of a beam, and then how every time you show certain this kind of vibration amplitude as function of time, then you can plot this kind of thing at different time, and then show this. For example, if a beam, right, at T1, you show this thing, and T2, you show another thing, right? So that vibration of XT1, right? And then oh, next one you show okay, there's certain deformation, XT2. So you basically use MECH to show at different time about this thing, and then use this kind of movie something and try to show it has this kind of vibration and function of time. This and then T3, right? And then this is a very basic the way you can make this kind of animation and movie, right? Of course, MECH can also generate the MPEG output file, right? Not only show in the MECH, so that this is something I told you MECH has very powerful, can do easy to do this thing with a piece of cake now. I can give you one example about my mechanical vibration now animation using MECH. I remember I do have this kind of example. I created if you look at our Canvas website, I think we do have some MATLAB code. The series of MATLAB code try to show you. I can add at least some animation for you to look at this kind of animation of a mechanical system, right? So this is something I do think is interesting and useful for all of you to learn how to do the simulation. Simulation now to visualize vibration as a function of time. Why? Yeah. How about this? How can you make it animation? Basically, in MATLAB, we already have solution, right? So what you need is you have solution and use MATLAB to describe at different time about coordinate, right? Coordinate at this M1, M2, and then draw this one. Draw this kind of square, rectangular or some square, right? And here, and then show T1, T2, and then using the one I show you, then you can generate this kind of animation. It's something. It's not difficult, I would say. And then, of course, once using this animate, right? Then you can there's some additional subroutine to send the output into the MPEG video, right? This is again, it's not difficult, but it would be interesting for all of you to think about how MATLAB can be useful. Of course, MATLAB has another one, MATLAB Simulink. I don't know if in the control system principle, some course you, the professor or teacher teach you how about Simulink, so that there's another branch of MATLAB Simulink, which is quite powerful to, the MATLAB Simulink can quickly build Simulink. It's a quickly build this kind of for example, certain mechanical vibration or something, or more complicated system is piece of cake now. So that's a thing. The MATLAB Simulink has a pretty good simulation for maybe mechanical vibration, so that there is I think it's a very simple now, right? You can try to look at some example and then easily do some simulation for mechanical system, right? So this is something I told you it's a piece of cake now. In old days, it's difficult. In old days, it's difficult, but now I think all the computer become so powerful. You can easily build quite sophisticated the model. You can create very complicated mechanical systems for things now, and then do the simulation. So the MATLAB has a lot more this kind of function, right? It's but of course it's more than what we use here, but at least give you some idea about the thing. And of course, you can actually, this is the exact solution. Now we have solved. On the other hand, how even without this exact solution in MATLAB, how can we do? This is the exact solution, right? You think solve the ODE by hand, but in MATLAB we can solve this one by numerical method. So how can we solve to get this result in MATLAB? I think we mentioned in previous lecture how can we solve this one using the ODE solver. With launch CUDA ODE solver, so that in MATLAB, so that there's basically this is an analytical solution, Why? For 2-degree freedom. But we can use this another numerical solution, right? Then we have a numerical solution, right? In MATLAB, basically is using you can use this kind of ODE solver. For example, like ODE 3.4 solver or something. There's a series of the solver. You can easily solve this one without using this thing, so that again, this is not difficult, but it's useful for you to look at this kind of thing. We do have ODE solver. You can hear before. Right. Sorry. So there's a series of ODE solver. Right? Once you specify the MCK mass spring system, and then use this kind of ODE solver to solve the vibration as function of time. So that this is ODE solve this non-different equation, right? So it describes our MCK in this kind of ODE function, and then T span, right, specify, right, from 0 to maybe 10 seconds and initial condition, so that you can easily solve this thing. Okay. Oh, this is one of example. Vanderpool, nonlinear. This is Vanderpool is one of a very classical problem. Vanderpool is a nonlinear electrical circuit model. Okay, and then you see we just use this one thing, ODE23 solve this Vanderpool. This kind of a thing, and then we can plot. So basically, OD we describe our mechanistic MCK in this function, and then T equals 0 to 20 seconds. This initial condition, and then we can get the result, time vector and Y response. Okay, so this is a Vanderpool. This kind of nonlinear ODE for the electronic circuit. Okay. VDP1. Evaluate the Vanderpool ODE. Did you know what was a Vanderpool? Huh? It's a nonlinear electronic circuit. It's one of a very oscillator. It can be this is here. Electronic is nonlinear, and then so that so MATLAB has a built-in function describe this nonlinear ODE. You see, just like MCK, mass MCK, right? And but this velocity term is nonlinear. Do you understand? It's nonlinear and then cosine. Oh, sorry, I should try to share with you. So this Vanderpool is a nonlinear system. You can look at this N, but this C is nonlinear and K, right? And then depends on this kind of parameter mu, then this nonlinear nonlinear stamping can have some very different kind of response. Okay, so that I told you this is one of quite sophisticated thing, right? So basically, we can reduce this kind of second order ODE into the first order ODE, right? And write down in the MATLAB, right? VDP1 is now having built-in function, right? And then you can solve this thing. Of course, one of basically this is described this kind of quite a complex nonlinear. There's a electrical circuit for the trial. Okay, this circuit. In our mechanical system, I think we will show you. Did you still remember about cell excitation system we showed in previous chapter cell excitation. Huh? You have some moving belt like a dot matrix printer, and then you move the motor, and then there's some friction force. Actually, this equation can be also described that the cell excitation system we show in our, do you still remember? There's some kind of a thing, right? They call some kind of negative damping. And then, so that this is, I think we already showed you about that thing. Did you still remember? Chapter 3? Cell excitation. Do you still remember that thing? So this kind of nonlinear vibration is somehow is quite common. I think we show you that nonlinear excitation, right? I think forgot chapter 3 or chapter 4. Huh? Oh, maybe it's not here. Maybe here. Chapter 4. Okay, chapter 4. Basically, chapter 4. For the nonlinear vibration system, then we have this kind of the issue, right? I think I'll show you this kind of phenomenon. This one, cell excitation, right? If you have some this kind of friction, right? You have a mass spring system, the friction, and then you will see this kind of this thing. Yeah, this is give you one of potentially negative damping. Okay, the friction force give you this thing. Okay, so that I just tell you this is you can see if you move this one, move this here, the right side here, here. So what's that? Huh? So you have m x minus mu y w and then plus k equals 0. And w is what? It's a mu n, right? So that this is something I tell you it's a kind of nonlinear system. Okay, so that you will show some similar behavior like I will just look at that van der Pol. You see, negative. This is something will give you some idea of a thing. Okay. Do you have any question for this thing? At least I told you this part somehow once the nonlinear somehow is complicated. I would say complicated behavior, but it's important to deal with how we can really understand this kind of nonlinear behavior. Why? Because in many times we do solve a real problem. Yeah. Okay, so let's start. We show you that the two freedom model has been practical for real vibration engineering to describe, for example, motor pump system, right? MECH1, MECH2, right? And packaging of instrument. And actually, I may show you about the packaging of 12-inch silicon wafer I got from a semiconductor company from Guangzhou. And then actually that is something I would say very complicated, sophisticated, this kind of system. I can show you. Let me see if I can show you now about this kind of real. Can I show? Okay, anyway, so I just tell you that we for this thing is something quite sophisticated, I would say. Let me see. I can show you this one through this check. I got this kind of a big package from Guangzhou, and then inside the package they have this kind of thing. Let me see if I can show you now. Uh-oh, I cannot. I don't know how to, if I can share with you. Oh, okay, you're right, you're right. I see. Okay, okay. Let me. I think I can share. Let me see how. Join. You don't need to use your. How I?
The screen is have a function to project your artwork.
Oh, really?
Yeah, in share screen. No, press on share screen. Then artwork, I can click this.
Oh, okay.
Yeah. Should have the mirroring function of your iPhone.
Let's see.
This one. Then find the zoom.
Oh, wow, this is a new. I don't know this kind of a new function. Oh,
yeah.
Oh, okay, interesting. Okay, it's interesting to. I just sent you this, but anyway, I show you here. I see. This is a big package, 12-inch thick wafer. Inside, they have this big thing, and then you have this kind of 12-inch thick wafer. And then they need this kind of very sophisticated packaging to protect during the shipping. It's a 12-inch wafer. Do you know how much this guy? How much? About 1,000 to 2,000 US dollar per 12-inch wafer. Inside we have about 200 chips, like our CMOS main sensor. But if you try to place order to use the 0.18 micron CMOS process, the whole wafer you place order, I guess probably $1 million. We just share this kind of a design. But anyway, as I tell you, this is something critical now for real product. Now packaging is because what? Silicon wafer is what? It's very brittle material. If you don't do this kind of basically it's a vibration damper. Energy dissipation, so that during the shipping you may have some vibration and shock, so that if you don't hear, your silicon wafer break into pieces. This is very important for real this kind of engineering, so that I tell you this is something inside. Basically here inside we have about 200 216 this kind of device here. For each one we have a thing to say. We have I did anyway. I tell you this is quite interesting. I never thought we can. Before issue, my PhD only handle 4-inch wafer only for our UST clean room. This is not too many professor can work with a 12-inch wafer. Usually 4-inch wafer for research, but this can be really used for mass production of semiconductor chip in your computer, smartphone, and even our CMOS sensor. For that, I tell you, this is something we have been working on this one for real, practical engineering research, so that give you a real example. Okay. Anyway, so it's something I do think it's interesting and useful. That you share about this real vibration engineering issue. Yeah, and of course another thing is once you have total freedom or anti-freedom problem, next is we want to what? we need to find some new coordinate system or generalized coordinate system, so we can decouple the this kind of MCK, this kind of different equation system, right? So that nothing uncouple, decouple, so that, for example, if we have a 2D filter model MCK with down damping, and then so that in this case, how can you solve this problem? Basically, of course, you try to describe this kind of MCK and N and K are symmetric, and then so that in general it's take time to solve this kind of thing. But of course, for example, we use this one as example, so that if you given M1 is 10 kg, M2 K1, K2, K3, the initial condition, M1 initially is 1 velocity and all these things, right? So that then we can solve this thing. So that, of course, for 2D filter, actually we have an exact solution. We can solve this kind of quadratic equation to get this solution, omega-1, omega-2, natural frequency, no more vibration mode, yeah. And then we can solve this one. So this is, I think, quite a simple approach. Of course, in MECH, how can we do that? Let me show you. In MECH, basically, it's we can do this kind of thing. We set M1, M2, K1, K2, and define. Let me quickly show you the. Basically, we define. You see, our M1, M2, and mass matrix, and Stevens matrix, right? And then what we do? We use EIG. EIG is the one we can try to solve for eigenvalue problem and produce our output eigenvalue and eigenvector. Well, if you enter the EIG matrix and then it give you V and D, why? V and D is the one we want to see. You see? Do you understand? So of course, you have a tool, so then they can solve this kind of eigenvalue problem. Do you understand? So that for this particular example, basically we can do it. We can inverse of n, and basically you can do things. Basically, we try to do. You see, now we use this kind of inversion, IMV inversion of mass matrix, mass by K, and then try to solve this one thing, EIG, and take square root. EIG basically is try to give you this kind of V and D. V and D. Now see, this is eigenvector 1. That means vibration mode number 1. And I don't know if I share this one or not. So this is a V. This is what we show in lecture note U1, U2, right? And then we have another is a D. D means this relate to what? Omega square. Do you understand? Remember this is we try to did you remember? So that this is omega square. This is so that we need to get some additional square root to get a solution. I hope you still remember about how we solve this problem. So we have square root. So that then get omega, so that we need to get this one thing. EIG of this inversion of n multiplied, CY is it, and then square root. So get omega. Omega is our natural frequency. Do you understand? So if omega 1, omega 2, so that do you understand here? And then of course, if you specify this kind of thing, that's another approach we can do is we try to here EIGAA, then we can VV and DD. Why? VV is related to the DD is related to this kind of omega 1, omega 2. Yeah. Okay. Do you understand about how we use MATLAB to get our natural frequency square? Basically, it's omega square, and then so that that is something important for. I don't know if I should. Basically, we just EIG eigenvalue problem and to solve inversion of this one is inversion, right? Basically m minus and k minus 1. Oh, sorry. M and k. So in MATLAB becomes in INV, inversion of m and k multiply k. So this is the MATLAB way, and then we put here, then we can get this. This is a eigenvector, vibration mode 1, vibration mode 2, right? And this is a omega 1 square. This omega 1 square, omega 2 square. Here. Do you have any question? So that it's this MATLAB have all these tools for to quickly analyze this problem. Of course, next one is of course we can easily try to conceive about this thing, right? So that of course MATLAB has another function. Remember, MATLAB only handles some number and look at the symbolic calculation. So that here next one I show you is solve the same problem, and what we try to solve in this kind of symbolic way. Basically, we define the symbol. We define the symbol, and then we solve this problem. Symbol doing that. We define the symbol, and then try to come with this kind of a solution in different way. So that I just tell you, MATLAB is powerful. And let me show here. Now I define, you see, symbol. Basically, we define omega MSPP P1 is a symbol. It's not number. And then we can try to manipulate this kind of symbol. Why? We're not handling number, we know it's symbol, it's symbolic, and then to do this kind of analysis. This is another quite important way. You see, our math matrix here, and you see, our symbolic math matrix is not number. It's a symbol. We manipulate this kind of thing, and then we can what? Do determinant. Doing that, we can DET MS. See? Maybe you get this something doing that, so that this is a polynomial. Sorry, I should not call it one. Anyway, so that the MATLAB has this kind of interesting symbolic tool, so that I can solve this one, and then of course we can solve this one. Now, basically it's something I would say interesting for you to appreciate the thing, one thing, and then we can do. I'm sorry again. So basically, we determine of this kind of matrix, right? 2 by 2 matrix become here, and substitute SUBS is replace this polynomial W by X. You see? So PP1, you see, X, W replaced by X, right? And then we can try to solve this kind of, you see, I solve this polynomial and determine omega 1 to plus and minus, plus minus, right? Omega. So this is the show how powerful is MATLAB to see. Basically, is what we learn, right? Plus minus omega 1, plus minus omega 2. Any question? Huh? Pretty advanced. MATLAB can do the same thing. So I just tried to show you the same thing. Now we describe in our lecture note, right? But it was a different MATLAB approach. Of course, EVAL is what? It is try to because we have become some symbol, right? So that we want to, if you want to calculate this thing, then we try to, you see, we convert this kind of thing into the floating point number, EVAL. Okay. Any question, Thomas? MATLAB, how? Yeah. Again, this is a MATLAB approach to describe about what we have described in previous chapter in different way, right? Remember here, once you have an MCK model, right, and I show you that we can solve this kind of equation motion and then analytically, right? So this is something I just show you this example, right? In this kind of a MATLAB approach. Yeah. And then of course we already in our MATLAB, so that we already show you this is a V, right? Remember VD, right? So that the V basically have two components, right? First component is this one, this is V1, okay, and V2 is this component, this one right here. This is here. And then D has a two component, right? Omega 1, omega 2, two nature frequency, right? So it equals this kind of eigen value, EIG, IG, and then this kind of inversion, IMV, and multiplied by K. So this is a MATLAB approach to solve this problem. Of course, with same approach, MATLAB is powerful. It's not limited to 2D feeder. If this is 100 by 100, 1,000, I think now your computer is pretty high speed and memory is enough, so you can easily solve very big problem, right? Which is difficult to do like 20 or 30 years ago. But that's why it's something you can easily, right, solve this thing. I can show you now. For example, if you want to solve something very big problem, this piece of cake now. Typically, you have what? At least, what's the memory of typical PC now? You can estimate how big the N and K you can handle. How big is the memory for typical computer? TB is something, right? Typically, I would say your memory, right, is maybe at least our 16 gigabyte or 32 gigabyte, right? So that you see, you can see, look here, how big is this matrix? This is M2 by 2 is very small. So how many bytes? So that if you handle, for example, n become the magic, maybe 100. You know the n become 100 by 100. So that you see, if I try to redefine here and then, so that you say it's now it's a, I would say must, 100 by 100. So that this is the it's still very small, so that it can easily solve the very big matrix. Why for real vibration engineering solution, even 1,000, I think also piece of cake. Oh, by the way, magic is built in the function. I mean, they give you the quite special kind of a matrix. They call magic. Now let me show you what's magic. Magic is n by n matrix construct from an integer 1 to n squared with equal row, column, and diagonal. Do you see? For example, magic 2. Do you see? Magic that means 1 plus 4 equals this the same. It's called magic. Do you see? So do you see? This is a magic matrix here. This 1 plus here. Do you see? So it's a quite interesting thing. Control from integer through here. Okay. Anyway, so it's and of course we can easily magic 3, right? Magic 3. Can you try to see? It's a a plus 3 plus 4 is 15. Why 15? 15. All right, so that you actually you can easily handle this big matrix EIG, for example. Okay, magic 100. You can see I handle this kind of big 100 by 100. It's still very easy to solve this one. But you can see if your matrix is not correct, you have a complex number. So that but typically our matrix is symmetric, so that you will not have this problem. Most likely it's a real number matrix, right? But this matrix is against the typical mechanical system matrix, so it's not symmetric. So the result will be not physically saying that that's something. I told you that something different. Yeah. Okay, so I think we do spend time to describe this thing. Yeah. Of course, another thing is torsional system is another quite important thing. So what kind of a torsion system we see in our daily life? Once a motor, once a motor, we have some engine. We have this kind of system, right? Motor is everywhere. For example, motor to control screen, or this a motor for control many things. So that we have motor everywhere, right? Motor for electric fan, and maybe some motor HVAC system, right? We have electric fan or some mechanical unit. So do you know what's every classroom office we have this kind of mechanical unit. So inside what do we have? Heat exchanger. We have some chill water, right? And then we have some electric fan, right? And then so that in this case we have a remote control or thermostat control this kind of fan speed, and also control this kind of thing, so that to provide cool air for our this kind of central air conditioning system. So that is the fan, right? So fan is electric fan is everywhere. Of course, once you have a motor or engine, so what happens? We have some vibration problem and noise. So that sometimes noise can be very bad, vibration and very bad. So that we need to think about how to solve the problem. Yeah, so of course, once you have motor, then we have certain kind of a gear or some kind of a inertia, right? And then we may have this thing, so that of course we can try to construct either one defeater, two defeater, or n defeater system to solve this kind of vibration problem. Then I can show you. You see, we do have some practical this kind of a problem in the real world, right? So in the real world, how can we solve this kind of vibration problem? What do you think? I just show you. Actually, I have a project. Try to do this thing so that you see. Let me show you typical step motor. So that we do have a vibration, and then typically, you see, vibration can carry this thing. So that is one of important thing I want you to observe.
The stepping motor has a 0.72 degree step angle to rotate with one pulse.
You have an inertial rotary mass spring system.
Because of this, when operated at a low speed, it repeats moving and stopping. This sometimes causes vibration. One of the major causes of the vibration is the one-step response characteristic. In this graph, the horizontal axis represents the time, and the vertical axis represents the angle. This shows how the stepping motor makes a one-step rotation. It does not completely stop after rotating 0.72 degrees with a one-step movement. It repeats damping by going forward a little past 0.72 degrees, and then coming backward a little, and coming back a little further before a complete stop. The portion going forward past 0.72 degrees is called an overshooting, and the one coming backward past it is called an undershooting. These overshootings and undershootings are the causes of the vibrations in the stepping motor. When the stepping motor is continuously operated, the one-step response characteristics are continuous too. In this graph, they are represented as continuous step response characteristics. When operated at a low speed, the motor repeats overshootings and undershootings before it stops and then moves one step forward. When it is operated at a little higher speed, the overshooting timing and the motor's forward movements are overlapped, making the vibrations more violent. The frequency at this time is called a resonant frequency. When it is operated at a much higher speed, the motor proceeds to the next movement before the overshooting and the undershooting occur. And so the vibrations are reduced and the operation becomes smoother.
So this vibration problem is very common. Even in 3D printer, you have vibration, right? So that I do have a UG project. It suffer vibration for the main this kind of a LiDAR. So you have a motor thing, so that the vibration is a very serious problem for many projects. I have a multiple project. Most of them have vibration problem. So this is something interesting, huh? Yeah. Okay, so that of course the key question now is how can we solve the vibration problem? Huh? How? What do you think? At least there's some damper. I already put here, huh? Some damper, right? Do you think once you have a torsional thing, then I show you there's a certain damper. Why you need to think about to buy this kind of thing. This PID is active vibration control. Before PID, you should think about how to add additional C, visco damper or visco elastic damper with some spring, right? So that this is the way we add additional damper to absorb the energy. Remember, we have told you so that this is a practical way now to solve the vibration problem. And I think, of course, beyond this kind of pure damper, there's a lot more solution. So there's for example, Mickey, not Mickey Mouse, MECH4750, the Japanese company has this kind of way to do the kind of vibration, motor vibration damper. They have their own way. They call coupling. They have their MECH4750 is one of I would say very good company. Then they try to make this kind of they call coupler, and then try to do this kind of vibration control. Mickey, this company is a pretty Mickey, not Mickey Mouse.
What is this?
No. If you look at they have one video show you their solution for vibration damping. Here, this one. So that they do have very sophisticated way for vibration control. So that this is again, Japan is very strong in robotics, so that they have a very sophisticated design. But they call it's not the damper; they call the coupler. So it's a different language used in Japan. Japan have that different word, MECH4750. Japan, that they call the coupling for mechanical vibration. It's a little bit different language, but I tell you that they have some thing to do this kind of vibration control. Metal disc coupling for vibration control. Oh, they have a series of products, okay, for this kind of vibration control. I will try to add additional thing, especially I thought they have one very good video to show with their product how they can really solve a big problem. Okay, and then this is just give you a reference, right? So that Japanese is very strong in this area. Of course, they have a precision engineering, right? Do robotic control precision machine for what? Semiconductor, right? Canon. They have a good stepper for semiconductor industry for fabrication of semiconductor chip. Because U.S. government tried to ban ASML companies to sell the stepper in China, so that I know even our USC Guangzhou campus, we bought the Japanese stepper for our 6-inch fat R&D fat. So actually, we also bought this kind of. We have USD have very good cleaning facility, so that it's something. It's cost a big money, and then we have this kind of stepper. Why for this thing? Why so that this Japan actually used to be very advanced in this kind of photolithography. You see, we have this kind of machine stepper ASML. We cannot buy the advanced extreme UV one machine 150 million. This is the old machine. How's that? US bank, including Hong Kong, we cannot. We have money, we cannot buy. Most than the ASML stepper. This is something we have. Okay. We have an ASML stepper. Okay, this kind of stepper have very sophisticated active vibration PID control using to minimize the vibration, because you need to look at some micron or nano fabrication. Small vibration it could be trouble for your for fabrication of your semiconductor or microsensor chip. So it's something. That's why in our first lecture we show you about that active vibration control system for this stepper. Okay, so that is something important. Of course, just show you. Although we cannot buy, at least show you how it's in UV. Right? This most advanced is in UV thing now is quite sophisticated. One machine you need like several Boeing airplane to carry all the components, right? And TSMC put at least 50 of 150 million US dollars. So this is a very sophisticated. Vibration is critical now to think about. You are making the nanometer, think no vibration, you can never tolerate some kind of vibration. So you have very sophisticated this thing. So this in this kind of thing. So do you think so that I just told you that if Hong Kong or Malaysia cannot buy, and then you think about how to contribute your knowledge to build our homemade, our own SML stepper, it's become a big issue. So that I tell you, unfortunately, now that even we have money, we cannot buy most advanced this kind of extreme UV system. It's banned. It's banned now here. Why so many advertisements? They have very sophisticated
of the lithography machinery for foundries like Intel and TSMC. In my video discussing TSMC's $28 billion capital expenditure, I briefly discussed their situation. Their CEO said in an earnings call that they can make 50 high-end EUV lithography machines a year. That's it.
But
Without
anyway,
those machines, the foundries cannot turn into $1 million lithography machines.
it's a very, very expensive and very complicated machine. Why? So that I tell you, it's very difficult now. So that you probably can never, we can never achieve by this kind of thing. But at least how you can try to think about this kind of very difficult, very precision machine, right? Is something not easy. Okay, so I think we around time. So that again, so today we give you some about the 2D feeder MCK model, and then show you the solution and use it in the MATLAB to do this kind of analysis about the natural frequency and vibration mode. I also show you about this kind of animation function of MATLAB. I will give you example how to create this kind of animation for 2D feeder, this kind of system, and then upload on our campus website. Okay, so I think for today's lecture, I don't know, do you have any question? Of course, if interesting, try to think about this kind of code-based online platform, right? That's something will be interesting. Okay, I think if not, any question? If not, probably I think that